Number 9 has a car that's rolling with a speed that they give you. It strikes a horizontal coiled spring and is brought to rest in a distance of 2.2 meters. What is the spring stiffness of the spring? So you have an object that's moving with a mass and a velocity, so it has kinetic energy. And of course the units are kilometers per hour. Then you have a spring over here where we don't know the spring constant, but we do know that it is displaced or compressed 2.2 meters to bring the car to rest. So the only way you can really finish this problem with what we've learned in IB physics is to use energy methods and to use conservation of energy. So at first, there is no energy stored in the spring. All of the energy present is in the moving car. And so the energy in total equals the kinetic energy of the car plus 0 for the spring. And so the kinetic energy of the car is 1/2 times the mass times the velocity squared. After the collision, the total energy will still be the same as it was before the collision. That's conservation of energy. And so this is assuming that, no noise or vibrations remove any energy from the situation. So the total energy after the collision with the spring and the car comes to rest, there is no more kinetic energy because it's not moving anymore, and it's just potential energy stored in the spring. And energy stored in a spring is 1/2 times k times the stretch, or the change in length from equilibrium squared. And so if energy is conserved, these two lines will be equal to each other. So therefore 1/2 times mv squared will equal 1/2 times k delta x squared. The 1/2s will cancel out. So k will equal mv squared over delta x squared, which is 1,200 kilograms times the velocity. And if you want, the normal units for spring constant are newtons per meter. So if you want to get k in the normal units, you've got to convert the velocity to meters per second. So 65 kilometers per hour, that's 1 kilometer over 1,000 meters on top, 1 hour, 3,600 seconds on the bottom. If you can do this conversion, you get 18.1 meters per second. So that's 18.1 meters per second. The velocity is squared. You divide by the displacement of the spring, which is 2.2 squared, and all of this will equal 8.12 times 10 to the 4 newtons per meter.